Hello there and welcome back. It's good to see all of you again. We're looking at 3.3 this time. Concavity, whatever. I'll let you figure that out. And the second derivative test. So you've already seen first derivatives, second derivatives, third derivatives. I don't think you actually had to do a fourth derivative. That's going a little bit overboard for us anyway. Concave just means it's curved. You could pour into something or vice versa. We'll look at some of those extremes that we looked at before and the points of diminishing returns for input-output models. Let's just get with it. Concavity. So if you're locating the intervals over where it increases or decreases, we did that with the first derivative test, and that helps to describe the graph. It helps to describe what's going on with whatever you're working with, profit, revenue, cost, and of course there are other things too. I just usually gravitate toward those. So all you need to do is first of all make sure what you've got for a function is differentiable. That usually is not a problem with business applications. Concave upward when it's increasing on the interval, concave downward when it's decreasing on the interval. So here are the two things you really need to remember. Concave upward opens upward, downward opens downward. Pretty simple. Keep going. So concave upward just means that you could pour water into it, or orange juice or something. Concave downward means it's upside down. You think of it that way. Of course, you can see the tangents there. You can see where the ones on the left, the tangents are getting greater. Tangents on the left are getting less. If you look at the actual numbers, it would represent the curves of the slopes of the tangent lines, excuse me. So here we go with the second derivative of the function. And I've outlined some here, but I'll just underline that just for even more emphasis. So you're going to take the second derivative of something, and that second derivative is going to tell you which way it's concave. If it's positive, it's concave upward. In other words, like this. If it's negative, the second derivative, then it's concave downward. Looks like that. Which means, in other words, that if it's got a positive second derivative, it's got a minimum. If it's got a negative second derivative, it's got a maximum. That's handy. So how do you do that? First of all, find the x values. This should sound a little bit familiar, where you got 0 or undefined for your second derivative. Again, just like on the last time, use those to get the test intervals. These numbers will divide the number line into several different sections. It's like you took your Jinsu knife or whatever and chopped the number line into several different pieces. Those pieces are the test intervals. So here, for example, is one test interval. Sorry, that didn't turn out too well. More like that. That's better. Okay. Test assign each test interval. So if this is the test interval you're working on right this instant, you pick whatever number you like in here at all. Just like in the last one when we were using the first derivative test. Pick any point in that interval that happens to be convenient or what attracts you. I don't care. So here's one to play with. What open intervals find that function concave upward or concave downward? Let's see. Well, no big surprise. We're going to differentiate twice. First, though, so we can use a power rule, we're going to rewrite the original function. I don't need to write this out because I've already done it in PowerPoint. Apply the chain rule to get the derivative. Clean that up a little bit with some algebra. Here's your first derivative. That's the start. What's next? Apply the quotient rule, of course. Simplify that. Simplify a little bit further. That looks a little bit better. That's easier to work with. Now what? Well, you can see it's defined for all real numbers. And you look at that and you say, wait, what about the denominator? Could that be a problem? If you look at the denominator, you have the 3 inside there. You're adding something that's squared. So that can't be negative even, let alone 0. You can't get a 0 out of that. If you actually try it, go ahead, try if you like. If you don't believe me, take x squared plus 3, set it equal to 0. X squared equals negative 3. X equals plus or minus square root of negative 3, which also means those are just imaginary numbers. So, since it's defined for all real numbers, and that's where f double prime of x equals 0, and where x equals plus or minus 1 from the top. The bottom is okay regardless of what you use. The top, set that equal to 0. And this is what gives you the positive or negative 1. Because you factor this as x plus 1 and x minus 1. When you set that equal to 0, 36 you know isn't 0, so forget about that part. Set this equal to 0, that equal to 0. There are your two x values. So that gives you 3 intervals, negative infinity to negative 1, negative 1 to positive 1, and 1 to positive infinity from your 3 critical numbers, or to your 2 critical numbers. Just put the number line into 3 different pieces. So there are your 3 intervals. Intervals are showing up here. Interval number 1, interval number 2, interval number 3. Now they pick these test values. You can pick something totally different. Maybe you decide, if I were doing this, I would pick an x of negative 10. Or in this interval, maybe you would pick 1/2. And maybe over here you would pick 100. And that's perfectly fine. All you have to do is take whatever number you picked in that interval, put in the second derivative to see again whether it's positive or negative or 0. Here you go, positive, so concave upward. Negative, concave downward. Positive, concave upward. It's as easy as that. What I would suggest, though, is not only take the first derivative tests and how you're going to use it, put them on a note card or somewhere you can easily find it. Do the same thing like this for the second derivative test. That way it's ready for you. Points of inflection. That's where the concavity changes. So down here, for example, this point of inflection is where you cut the graph of this curve if you want a concave upward section and a concave downward section. This is where the split, where the change occurs. If you were going along this curve, you concave upward until you get there. Once you get beyond it, it's concave downward. Similar here, concave downward up here. When you get there, the rest of it's concave upward. Those are points of inflection. Another one, upward, downward. Point of inflection is where that changes. And just a note there, it's where the concavity changes. Nothing else, don't get it confused with anything else. The point of inflection is where the concavity changes from upward to downward or vice versa. To get those, you only have to find the values for which the second derivative is 0 or undefined. A 0 and undefined ought to start sounding familiar. 0 or undefined for the second derivative. And those will give you points of inflection. Next, an example to look at. So of course you write down the function, make sure you got it right on your paper. To find the first derivative, of course you can't find the second derivative without getting the first derivative first. Here's your first one. Take the second derivative. What are you going to be looking for? Going to factor, because this is the easy way to find out which values are 0. There will not, in this case, be any undefined ones, because if you notice up here, the function itself is a regular polynomial, which means it doesn't have any undefined points. You can use any real numbers there at all. The domain is all real numbers. So when you get down here to the second derivative, we can just factor this out, set each one of these factors equal to 0. Of course, this is silly, you don't set that equal to 0. But you do set those two equal to 0 to get your critical points. That gives you 2 critical points. Remember, the critical points refer to what the x values are, give you your second derivative as 0. We've got 2 critical points, so we've got 3 intervals. You're cutting the number line at 1/2 and at 1. Gives you 3 intervals. Put any value you want to in here. Say you pick a -5. Put that -5 in your second derivative. If you get a positive value, then it's concave upward. If you get a negative value, it's concave downward. And you check that for all 3 of those intervals. Here's a picture of what you've got, along with those critical values that you found at -1 and -1/2. Remember, 3 intervals from, where's my cursor? Okay. Here's one interval. Between these 2 is another interval. And back here is the third interval. So the second derivative test. is a way of finding minimum and maximum values. If it's concave upward, it'll have a minimum. If it's concave downward, it'll have a maximum. Real simple. Once you get to that point, it's real simple. So here's a fast one, something to put on your 3x5 card or wherever you keep your notes. So, first derivative is 0, and second derivative is on an open interval, contains some x point. If that second derivative is positive, then you got a minimum because it's concave upward. If it's negative, then it's concave downward, and you got a maximum. If the second derivative is 0, the test fails, and this is supposed to be a frowny face. In that case, you have to use the first derivative to figure out whether it's a relative maximum, relative minimum, or none of those at all. Here's another example. Another nice one, obviously, because it's a regular polynomial. So first of all, you get the first derivative, and as sometimes happens, it's handy to factor that out. You can see that you've got 3 critical points, 0, -1, +1. The 0 comes from this part set equal to 0, and the 1 and -1 come from setting that equal to 0, because when you factor it, 1 plus x and 1 minus x, and setting this equal to 0 gives you this, setting this equal to 0 gives you that. Only critical numbers of that. Using the second derivative test, you can see your points and the signs at those points, and you can see what you've got. Relative minimum, test failing where it's equal to 0, maximum, and you've got some information there for you. So 0, 0 is a point of inflection because it changed from positive to negative. Diminishing returns. So this, you would most likely be talking about profit, for example. When does your profit start slipping? So we start with a function, and this represents outputs. So for example, this might, where am I? There we go. This might represent the revenue, for example. And we want to see where the revenue stops increasing and starts decreasing. So we've got this in dollars as opposed to euros or something else. There's a graph of it. If you can graph it, that's really handy, because that, along with the calculus, can give you an idea of what's really going on. There's the concave upward to concave downward. That means you got a point of inflection in here. There we go. There's our point of inflection because it goes from upward to downward switches. And your second derivative test can show you that with the intervals. You can see what's going on there with input in dollars. I'm guessing, I'm not a business person, I mentioned that. It occurs to me that this input in dollars might be just another way of saying revenue. That's my guess. So here's a model, and these are the sales. So that would be dollars input, it's money coming in. Find the point of diminishing returns. So you ordinarily would think the more of these you sell, the more money you get. But there might be a point at which you don't get as much money as you used to by increasing your sales. So first, get the derivatives. There's the first derivative. There's the second derivative. And just by setting equal to 0, you can see where the second derivative is 0. X equals 20. There's your picture. You can see that the advertising costs are on the bottom, and the sales that you're interested in mostly are on the vertical axis. Notice that the sales are increasing faster, faster, faster until you get here, and then the sales start leveling off. So you have to ask, as a business person, is it worth going beyond this point? Maybe you'll have to look at the profit function. Maybe you'll have to consider, do the costs maybe decrease after that point? A lot of things to think about. That's your job as you learn more about the business. And last of all, so the product has diminishing returns after $20,000 you spent on advertising. So you're going to have to look at that $20,000. Where am I? Oh, here's $20,000. You're going to have to look at this. It's an eyeball. Look at this and decide for your business whether it makes sense to spend more money on advertising. Yes, you're getting more sales, but you also have to look at the bottom line, because to advertise costs money. What is it doing with the profit? Are you still getting more profit, or is it going down? That's your job. And my job is to check out here and leave it to you to do some practice. Signing out. Take it easy. Bye-bye.